Bismillahirrahmanirrahim. Assalamu alaikum. In our today's discussion, we will be discussing multi-level sinusoidal pulse width modulation inverters. As we know that basically there are four different types of inverter topologies available. One is Cascaded H Bridge multi-level inverter, that is we are going to discuss. But there are also three other inverter topologies. So the point of our today's discussion is Cascaded H Bridge multi-level inverter. The other three types are neutral point claimed multi-level inverter and modular multi-level inverter, modular multi-level inverter, and diode claimed multi-level inverter. So today we are going to discuss cascade H bridge multi-level inverters. This is our topic of discussion. All right. So in our previous lectures, videos, we discussed about bipolar inverter, that was a two-level inverter, and we also discussed unipolar inverter, that was basically three-level inverter. But sometimes we need to go for higher levels, maybe for 5 levels, 7 levels, 9 levels. So these are called multi-level inverters. According to some books, multi-level inverters start from 3 level, whereas in other books it is quoted that the multi-level inverters start from 5 level. So today we will discuss 5-level multi-level inverter. For multi-level inverter, you need to use multi-level SPWM techniques. It means that now you need to explore multi-level PWM techniques that you will apply on the inverter models. Okay. In bipolar inverter for two level, we require one sine wave, one triangular wave. I quickly repeat. In unipolar, you require two sine waves, one triangular. But for 5 level or for 7 level or for 9 level, as you increase the levels, you will require more number of carrier signals or more number of triangular signals to implement that topology. Alright, in multi-level SPWM technique, there are two approaches. One is the carrier disposition PWM, disposition PWM, another the phase shifted PWM. In carrier disposition PWM, there are again three types: alternative phase opposition disposition, phase opposition disposition, and phase disposition. These are different types. Now, as per literature review, this phase shifted PWM techniques offers more total harmonic distortion as compared to carrier disposition PWM technique. So our main area of focus will be carrier disposition PWM technique. In this, we will compare the results of APOD, POD, and PD, and we will analyze that what are the results on these different approaches. All right. Okay. Now, basically, this is APOD, alternative phase opposition disposition. This is POD and this is IPD. First, I want to clear IPD. In phase disposition technique, first basic rule is that for n levels, you require n minus 1 triangular signals. If suppose you are working on 5-level multi-level inverter, you require n minus 1 means 4 triangular signals, 4 carrier signals. If you are working for 7 levels, you require n minus 1 means 6 carrier signals or 6 triangular signals. So for n levels, you require n minus 1 carrier signals. Okay, and there will be one sine wave. One sine wave will be required. In IPD, as you can see that all the carrier signals are in phase. They are in phase. So this is the phase disposition where all the carrier signals are in same phase. Okay, this is called IPD. You can clearly see from the figure. Okay, and the other technique is POD, phase opposition disposition. And this technique, the carrier signals above the 0 point, above the reference line, the carrier signals above the reference lines are in phase, whereas the carrier signals below the reference lines are 180 phase out, phase shift with those which are above the reference line. So this is POD. I again repeat, in POD, all the carrier signals above the reference point, above the 0 point are in phase to one another, but they are 180 out of phase with those which are below the 0 line are reference line. Okay, this is called POD. Other is the APOD, alternative phase opposition disposition. In this, nearby, adjacent, all the nearby are all the adjacent carriers are 180 out of phase. Now see, this carrier signal is 180 out of phase with this, and this carrier signal is 180 out of phase with this. So all the near carriers are 180 opposite out of phase. So this is called APOD. So we discuss APOD, POD, and IPD. And now I want to emphasize on one very important formula for conventional cascaded multi-level inverters. I want to emphasize over here. I want to make this point very clear over here that there are basically two different topologies. One is conventional cascaded multi-level inverter, and other is the modified cascaded multi-level inverter. One is a conventional, and other is the modified multi-level inverters. MLI, multi-level inverters. Okay, in conventional, this formula is very important. For you require n minus 1 over 2 H bridges for n levels. If suppose n is 5, it means you want 5. N is 5. Suppose n is 5. It means you want 5 level multi-level inverter. So you require n minus 1 over 2 H bridges. So this will be equal to 5 minus 1 divided by 2, which is again equal to 2. So you require 2 H bridges. And we know that in 1 H bridge, there are 4 switches. So for 5 level, you require 2 H bridges. And in each bridge, there are 4 switches. So together you need 8 switches. 8 switches to implement conventional cascaded 5 level multi-level inverter. So you require 8 switches to implement conventional cascaded multi-level inverters. So this point should be clear. And similarly, if you are working for 7 level, so 7 minus 1 over 2 will be 3. So you require 3 H bridges. So in 3 H bridges, in each H bridge there are 4 switches. So altogether you require 12 switches. In conventional cascaded multi-level you require 12 switches to implement 7 level. And similarly for 9 level, n minus 1 over 2 means 9 minus 1 over 2 means you require 4 H bridges. And 4 H bridges means you require 16 switches to implement 9 level. So one point should be noted over here that as you are increasing the levels, your switching complexity is also increasing. This is the biggest disadvantage. As I quoted over here that for 9 level, you require 16 switches, 4 H bridges. So controlling 16 switches is not easy task. Microcontroller may not be able to control properly 16 switches because of the serial processing. So again, you will need some kind of a robust controller, maybe FPGA, to control 16 switches simultaneously. So you should notice this thing that in conventional, the biggest disadvantage is that as you are increasing levels, switching complexity is increasing very fast. And this is the biggest disadvantage. Though this is the advantage that as you are increasing levels, the total harmonic distortion will decrease, but at the cost of switching complexity. And in conventional, the biggest disadvantage is the switching complexity grows very fast. So what is the solution? Researchers focused that we should move to modified MLI. We should move to modified multi-level inverters in order to implement conventional cascaded H bridge multi-level inverters. Okay, what is the difference between modified and conventional? The difference is this, that in modified we will try to optimize the number of levels, but also we will try that the switching complexity should not increase that much. Like in my thesis work, I have tried to implement 5 level multi-level inverter with only 5 switches, whereas in conventional you require 8 switches. You require how many switches? 8 switches. So the advantage is that the same percentage of THG is there. In modified and conventional are verified, there the same percentage of THG is there, but the advantage was that switching complexity is reduced. In 7 level conventionally you require 12 switches. You conventionally require 12 switches, but in modified I have tried to optimize it and I have reduced up to 6. And in 12 level, in 12 level, in 9 level you require 16 switches, but in modified I have tried it to implement with 7 switches only. So the main agenda is to explore modified MLIs. Main agenda is to explore modified multi-level inverters and to explore these, because in this switching complexity is reduced. If the switching complexity will be reduced, then controller complexity will also reduce, and certainly gate drive requirement will also decrease, because if number of switches will be less, then gate drive circuitry will be also less complicated. So these are the advantages. That is why modified MLI is much better, and it's a good area to focus rather than conventional. All right. Okay. So in my next video, I will be discussing how can we implement basically uh, how can we implement 5-level multi-level convention inverter. We will first understand implementation, understanding the circuit diagram, understand the PWM technique of 5-level multi-level inverter in our next video. Thank you very much.